Hi, everyone. I'm your host, Lori Kretschmar. We're here today at the Viridischem webinar on green chemistry. What does it mean today for industry sectors? So we're just going to jump right in. We are so pleased to have all of our guests and attendees today. Everyone comes from many, many time zones. Thank you for making time to be here today to talk about green chemistry. We're pleased to have two excellent industry experts. That's Dr. Yuan Chao Rao from Dow and Dr. David Constable from the American Chemical Society's Green Chemistry Institute. And before we hear from them, we're going to have a brief introduction from Viridischem's CEO, Neelam Vaidya.
Thank you, Laurie. Hello, everyone. Thank you for joining us for our first webinar. I hope you'll be joining our future webinars as we schedule. Before we start, I wanted to give a very quick introduction to Viridischem. We launched Viridischem in 2014 with the primary goal of developing software products that can help reduce global pollution. Specifically, we wanted to develop products that can enable scientists to make decisions that will minimize the use of toxic chemicals, resulting toxic waste, and help them develop less toxic products. Our focus is mainly product development, and we want to provide critical toxicity-related information to the R&D scientists who are responsible for deciding what goes into the products and what chemicals should be used during product development. Today, Viridischem has built the largest toxicity database with 93 million chemicals, 48 properties per chemical. And we collected the data from databases provided by the governments, research organizations around the world, and we extracted the data from technical papers and regulatory lists. And some of the companies have shared their non-proprietary data. We curate this data constantly using in-house AI-powered tools. And this is an ongoing effort, and we update the database as the new data becomes available. And we have been successful in executing prediction models to fill the data gaps that experimental data is not available for. And we can actually execute these models on demand with results within seconds. As a result, our products can be, which is a chemical analyzer that can be used during drug discovery to study the potential health and environmental risk of new molecules and identify less toxic analogs and metabolites even before you start the R&D. Toxicity awareness of the chemicals during product development leads to processes with smaller toxicity footprint, minimum toxic waste, and avoid the late stage changes. Chemical analyzer can be used during product development to select less toxic chemical raw materials. And when you are choosing the product development route, it can offer toxicity footprint consideration as an added factor for decision making. EHS and product stewardship departments can monitor the global regulatory compliance issues and build the safety data sheets of the proprietary chemicals. While the lab safety groups can connect the tool to their inventory system to quickly identify and isolate fire hazards, corrosive chemicals, or the chemicals with health issues. Educators can use the product to teach students the relationship between the chemical structure and its functional and toxicological properties, and show how the small structural changes can make a big difference in toxicity of the chemical. And the young scientists can use this product tool to understand the toxicity of the chemicals and select the less toxic alternatives provided by the tool. Our chemical analyzer is available as an interactive tool as well as through API interface. And we hope to partner with reaction analytics and lab productivity tools companies to, so the scientists can get this information throughout their product R&D work. I hope you like what you hear. Please go to our website for more information. Thank you.
Yes. Thanks, Neelam. And our website is, I think you all know, it's viridischem.com. So I have a brief introduction about each speaker. We'll hear from each speaker, and then we'll have Q&A at the end. And if you have questions, you can type them into the chat box, and we'll try to get to as many as we can later. So we're going to start with Dr. David Constable. Many of you know David. He is Science Director of the Green Chemistry Institute, and we're honored that he's also a technical advisor to Viridischem. Then we'll hear from Dr. Rao. She will talk about how sustainability efforts affect an energy-intensive manufacturing company like Dow. She'll also discuss how green chemistry drives product innovation in the packaging, industrial, and home and personal care markets. Now, one note before we jump in: due to Dow's policy, Dr. Rao's portion of the webinar will not be recorded. She has agreed to answer some questions during the Q&A. So if you're listening today and have questions for either speaker, please type them into the chat. And with that, we're going to turn it over to David Constable. The floor is yours, and just it looks like you can start whenever you're ready. Thanks.
Thank you so much for your introduction. And I'd like to welcome everybody to this webinar. Some of you I recognize in the participant list may have heard some elements of this talk. I'm going to breeze through this at a breakneck speed. The slides will be available later on, and the recording will be available. So my charge today is really to take a very broad look at green and sustainable chemistry challenges and opportunities in industry. And I always like to start out with this quote about the perfect uselessness of knowing the answer to the wrong question. And I think as scientists and engineers, we've been asking many times, particularly when it comes to green sustainable chemistry, the wrong question. The current situation, as I see it, and this is my opinion, is compliance. In most companies are in the state that they're in is that they focus on compliance, and that's sort of the minimum base where they start everything. And so obviously addressing chemical exposures, building in safety, and so on and so forth. So looking into green sustainable chemistry solutions are oftentimes very difficult, and we have been in a situation of status quo for quite some time. Again, that's my opinion. Sustainable chemistry opportunities. The industry needs to develop more sustainable feedstocks. Currently, it relies heavily on petroleum. I'll talk a lot more about that. We need to think about substituting the high hazard materials, the high volume chemicals that we use routinely, and substitute them with lower risk materials and lower risk process technologies. Whether you realize it or not, from many things that you use on a daily basis, they all come from petrochemicals, or they come from this periodic table, which as a chemist I always like to show. And what's different about this is to showing that elements that are really important to chemists, such as the platinum group metal or precious metals in the center of the periodic table, or those on to the right of them, which are elements that are very important to electronics. These elements are what are known as critical elements. That is that the supply chains are difficult and come with a lot of environmental impacts and in many cases societal impacts. And going forward in the future, we really have to ask the question, is our current extraction, processing, and use of these materials being done in a sustainable fashion? If you spend any time looking at it, I think the answer to that is no. The only way that we're going to get out of the current situation, this compliance and the situation where we're using non-sustainable materials for everything that we make, is to think about how we design materials differently and using new materials. Chemists, I think, pride themselves on being innovators and making new stuff. So let's parse that a little bit and think about, this is the amount of chemical space or the space available to a chemist to innovate in. This is the number of molecules that have been discovered. So 10 to the 60 versus 10 to the 8. This is the ones that are available commercially. So 14 million. And this is what is on the EPA's list of chemicals of arguably regulatory concern. and they encompass they encompass all of the materials that are on the market commercially, and particularly those in the high volume category. So my point being is that we have this huge opportunity to innovate as chemists, and I would argue that we don't really do that. Much of what chemists rely on is iterative chemistry. That is chemistry that relies on basic synthetic structures that we are deriving from the petrochemical feedstocks that I showed you very early on in the slide, and they represent the core molecules or frameworks that we build on. In 2007, the Department of Energy said, let's take a look at the potential for bio-based and renewably procured materials to become our new framework molecules. And I've circled some which are now being seen and used commercially at not large volumes, obviously, but at big enough volumes to support growing companies. Point here being is that there's a lot more opportunity to investigate how these particular molecules can be used. So one way to think about that is that much of what we get agriculturally is like a glucose molecule, so a sugar, or it's a starch, or it's a protein, or something like that. And then the trick is that something like glucose isn't really synthetically useful or that interesting. And to synthesize around a glucose molecule, many times we don't do that well. It requires a lot of mass and energy in a process to change and manipulate that molecule. So what we want to do is move up to something like a pyrrone, which has a number of synthetically interesting areas of a molecule that a chemist can build on. So this is just an example I showed in the previous slide, a triacetic acid, lactone. And you can see that by innovating around this molecule, you can get to various high value or commodity chemicals. And again, this is what the Department of Energy did in its 2007 report. It showed all these different pathways. And I would argue that we need to be moving as a chemistry enterprise towards that kind of direction, which makes use of these framework molecules. And ultimately, we want to think about bioprivileged molecules. So in pharma, we talk about privileged molecules. The difference in pharma is that where you see oxygen on these molecules, in pharma, the molecules all have nitrogen. And that points to another difficulty that we have in using these molecules, is that oxygen isn't always the molecule that we are used to using or synthesizing around or removing the functionality. And again, to remove that functionality is actually quite different. So we have to maintain the functionality and innovate in new directions to get new molecules that we don't have to change dramatically in order to get them. We also have a lot of work to do around the chemistry technology that we use to make these chemical transformations, and ultimately to move towards more process efficiencies. So we need to reduce complexity of operations and things that are laborious. We want to get away from this idea of disposing of large amounts of waste. We want to become more circular. We want to think about materials and reagents and the waste that they generate. And we need to think about safety, both physical safety and personal safety and environmental safety. So technology has a very key role to play in ensuring those things. As chemists, you can't argue with the fact that chemists operate on precedent, and they also operate on very old chemistries. In other words, most of the chemistries have been designed to transform molecules on this petrochemical framework molecule. And if we're moving towards newer molecules, we need to have a different set of reactions. There's also a lot of problems with the existing reaction space that we're using, or the types of reactions we're using. This is a list that the Green Chemistry Institute Pharmaceutical Roundtable first came up with in 2007, and again in 2015. But there's a lot of work that needs to be done to change the chemistry reactions that we are using as chemists. Back to chemical technology, batch reactors, distillations, crystallization have been around for a very long time. We need to begin to think about how we can modularize and reduce the footprint of our process technology. So here are some examples. Here are some more in terms of different approaches to reactors, where the reactions take place. Most synthetic organic chemistry happens in a batch operating environment and not in flow, and that's arguably not a very efficient way of doing chemistry. Another hidden element of chemistry technology is really around separations. Separations account for the production of a large amount of waste. This is especially true in bioprocessing, where we have huge volumes of water to remove, and heating water is not a good idea. So we need to think about how we can introduce better separation technologies into the chemistry enterprise. So again, we're not producing large amounts of waste, and we're also not consuming enormous amounts of energy. We need to think about solvents, because in the batch chemical operating industry, and really in petrochemical industry, there's a large number of solvents and a large amount of them, and solvents that are really hazardous, and we need to shift our reliance on these kinds of solvents. In terms of bioprocessing, we really need to do an awful lot of work, because we're nowhere near getting to the levels of mass and energy efficiency that a petrochemical industry operates at. Again, we're not very good at the volume efficiency of the reactors. We're not very good at separations. We're not very good at downstream processing and isolation. So there's an enormous amount of opportunity and challenge in moving to bioprocessing. These are some of the grand challenges, as I like to call them, of sustainable chemistry. And I've talked a little bit about exploiting the chemical diversity, but we really do need to exploit that more dramatically than what we're doing right now. Synthetic biology should be seen as a chemist as just a tool for delivering very selective, chemoselective and enantiomeric selective reactions to the chemist's toolkit. New reactions that are focused on the biologically derived molecules, lower energy conversion of CO2 to a variety of chemicals. In order to do that chemical upgrading, hydrogen is essential, and currently 95% of hydrogen comes from steam reforming of methane, which is not sustainable. So we really need to get to this idea of green hydrogen production and green ammonia production, and so on and so forth. And finally, closing the materials loop and circularity. It's really come into vogue in the last few years. We are really at a nascent state in circularity, and we have an awful lot of work to do. So one of the points I always like to make is that the chemistry and chemical engineering communities are arguably the best situated to make a profound impact on the sustainability of the world. But green and sustainable chemistry is more than just hazard and pollution reduction and elimination. It's much greater, and we need to think about these things from a systems perspective and from a sustainability perspective. That is a triple bottom line perspective. Innovation is clearly needed in this space, in the chemistry enterprise, and innovation which again is green and sustainable and is done with a systems level view. Early design is the best way to do it. So we need to teach students how to do innovations, how to think about the chemical transformations that they do from day one. And I could talk more about that at length. There's a lot going on in this space. I don't mean to say that there isn't, but I would definitely say a lot more needs to be done. And there's lots of tools available to help you along with that. I'd like to end with a shameless plug for our GC&E, which is coming up next year. We just ended our last one, but I hope to see you all at our conference next year. And thank you very much for your kind attention. I'll look forward to your questions in a few moments.
Great, thank you so much. That was great. And if any of you have questions already, please type them right now into the chat, and then we'll get to them. So we're about to turn off the recording. We're going to hear from Dr. Rao at Dow, and we're starting our Q&A section now. Thanks to those who've already put some questions into the chat. And here's a first question for you, Dr. Rao. You gave us some great examples. We wondered, Can you talk about a specific project at Dow that you think has benefited the most from green or sustainable chemistry?
There are too many examples.
Do you have some favorite ones or recent ones? We'd just love to hear a few.
Yeah. Actually, that's part of the purpose of the last slide. And I contributed personally to 2 of them. So my favorite one is the sunscreen booster. So we didn't have time to go to the detail. However, that's to me is a very clever way to provide a safer material. So instead of we make certain type of material to boost the UV blocking, the way we take it is we using a different way to think about the optics, really to utilizing the scattering and the scattering of natural material in a different way to be able to solve problems. So I think that's an example about you have to think about design for sustainability. We should just, sometimes you need to be open-minded.
Good. Well, thanks for that. And Dr. Constable, we have a very specific question for you. You talked about how there's a big need for innovation, and one of our attendees today wondered, do you have some innovation ideas in the area of chemical waste management?
So in green and sustainable chemistry, the hope is that you limit the amount of chemical waste that you produce by the way you design your synthesis route and your process that goes along with that. If you have done that to a minimum, then the options are really dependent upon what you're making. And there's a lot of pollution prevention ideas that one gets to when it comes to waste. So simply segregating waste streams out of a process can, in some cases, allow you to resell something or to isolate something from a mixture is far more difficult. So if you can segregate that waste stream and use that in another process, that's what's known as mass integration across a large chemical plant. That's another idea for chemical waste. When there is nothing left and it's only chemical waste, your options really are limited, I think. And it really, again, depends on your waste stream. So I have to give you a general answer to that question.
Well, thank you. We have another question for Dr. Rao. So this one's very specific. One listener in particular heard your comments about PLA versus PS, and that person wondered, what was the boundary of the life cycle assessment in assessing the environmental impacts of PLA versus PS, and did it include end-of-life considerations? Also, I wonder, is this something that Dow has talked about much? Could we find something on the website, for example?
Okay, so first of all, that example has nothing to do with Dow. We're not making polystyrene,
Okay.
We're also not making PLA. So I simply just want to present a example to illustrate the complexity of the problem. So the person asked about the life cycle analysis. So that one, the paper, you can read the paper. They did the fairly thorough life cycle analysis. Of course, if you think about life cycle analysis, is really to think about the energy raw material go in and the energy raw material or waste material come out. Basically emission versus the input energy and the raw material. So then you balance it. But I actually want to argue that is only the ecological side of the analysis. The other is sociological. This probably Dave would agree that when we make the material, there are different processes, some process that present a higher, for instance, hazards to our workers. So those are the things that all need to be taken into consideration. To me, it's very, very challenging, right, to get to the true, the best solution. But I want to say is we do need to be mindful this has to be a dynamic process in the sense that it is going to be, that's why I think it has to be coordinated because the energy input is completely, the calculation of energy input completely based on what type of energy you use. So if you're already using like renewable energy, and then you don't have carbon emission problem, right? I mean, not completely, but that's just a part of the equation.
Thank you. Well, here's sort of a philosophical question. So, well, actually, this is for both of you, but maybe we can start with David. The question is, do you think companies, well, I'm going to make it a two-part question. Do you think companies are willing to give up a bit of profit for trying new and more sustainable processes? That's the question, but I'm going to add to it because I used to work at Fortune magazine and was into business writing. And how do we incentivize companies like Dow and other companies to really do more in the area of sustainability? So can we start with you, David, and then you, Yuan Chao?
So I would say it's really a false choice because if you design a new product using principles of green and sustainable chemistry or using the ideas that we've discussed today, the overall delivery, use, and end-of-life considerations will make that a economically preferable solution. In other words, you don't have to give up profit. And arguably, if you design it that way, from a function-based perspective. So great example that Yung Chao talked about in the addition of a natural product to a sunscreen, right? And you increase the functionality of that material so it has much better performance. And I'm sure that they were able to do that without increasing the price of the product. And you can do that in a variety of ways. Use less of it perhaps, or so on and so forth. But the bottom line is that if you are following these principles, you shouldn't have to make that choice.
Wow. Dr. Rao, do you want to add anything? Do you have any comments?
Sure. I mean, that's the company's thinking every day, right? So as an R&D scientist, we just want to do sustainable or green chemistry. But however, the company also needs to be able to survive. So I do feel it has to be a hard choice, and the cost need to be distributed. So like, I mean, home personal care industry is a perfect example. We do voice of customer to ask the ordinary people how much they are willing to pay for sustainability. And then we will use that as a guidance that we do as much as possible, right? Because if the company cannot make money, it's not sustainable, then this good company going to disappear. So I think, of course, maybe more effective is the regulation. I know Europe has been doing a great job in setting examples and also maybe looking at the carbon tax and so on. So I think that need to be continued. Yeah, hopefully the US can also have something in place that promote or incentivize the company to do more.
The same person who asked that question added that their thinking is that sometimes when something is more sustainable, it becomes more expensive for the consumer, which could be an elitist issue. And this person says, if I want to buy biodegradable soap, it might be 3 to 5 times more expensive than non-biodegradable, and that makes it hard for people who don't have a lot of discretionary income. And David, do you want to comment on that about what about from the consumer angle? How do we inspire sustainability on a grand scale so it's not hurting the consumer?
So this is a very long discussion, to be perfectly honest with you. Couple points I'd like to make. There have been numerous studies that have looked at the market for greener or more sustainable compounds. And what you see is somewhere around 8 to 10% of the market. and this has been replicated, I think, for like the past 25 years, I've been following this. 8 to 10% of the market is willing to pay more. That means that 90+% of the market is unwilling to pay more for a greener or more sustainable approach. And in many cases, because green has, there's been associated with greenwashing, people are less inclined to buy it if it's more, right? Because they say, I will not get the performance. Even though the performance might be superior, it has this reputation that you're taking a hit on performance. So I would argue that, what we need to see as a transition to understanding that doing things from a green, sustainable perspective requires a product to be higher performing in both actual technical performance, but also in economic performance. And it's just going to take time for that transition to take place. But if you design from first principles to make it greener and more sustainable, it will be less expensive to produce it, and it should be equivalent in terms of what the asking price is to the consumer.
And how can we accelerate this process that will take time?
I don't think you can. I'm sorry.
And Neela might have comments. And Dr. Rao, do you have any comments about
Yes, I do.
Great.
Yes, actually, I'm going to present this as the grand challenge for chemists, because if you think about why the petroleum-based product is so much cheaper, is because all the chemistry and the engineering put together, developed in the past century. So the different feedstock and how can we make it more affordable is really the question for this generation. So that's what I think indeed we need to focus on is, for instance, why bio-based material has to be more expensive, right? So starch is not that expensive actually. I mean, I learned a kind of surprise. It is less than $1 a pound, 50 cents or so, which is pretty much the same as a polyethylene, polypropylene. And of course, the property is different, right? Polyethylene are able to really give a much better property compared to starch, but that's where I think the R&D effort can come in, is to first lower the cost of all this feedstock, and the second is consider the most effective way. So enzymatics catalyst I think is a perfect example. The biological community are very good at very specific, very high yield. And so we just need to define, I think it's a good time to define those specific challenges. And I think the federal need to support the development, technology development in those areas.
Oh, great. So we have a grand challenge here.
Can I just say that while I agree with everything that you've said, I'm just saying from a societal perspective and a people perspective, you have to train people to think this way. And that is what is going to take time. Green sustainable chemistry is how you practice chemistry or chemical engineering and allied disciplines, right? And you make choices. And right now, the system is all based on and organized around making choices with existing materials. So to get people to start thinking about other things and other possibilities is really, a huge challenge.
Okay, well, the younger generation in particular will really need to fight that one, right? We'll get a couple more quick questions in, and then I'm going to turn it over to Neelam, and we might have a quick on-screen poll for all the attendees. David, someone wanted to know, are green chemistry principles applicable even for large-scale industrial synthesis?
So what I would recommend is that you go to our website and look at, go to the green chemistry principles section, and in there is a brochure called Sustainable Design Principles for Green and Sustainable Chemistry. In there are 48 principles of chemistry and engineering, and they are absolutely applicable to any type of scale that you want. The point is that it's a combination of chemistry and engineering that needs to be applied. And if you do that mindfully, you will end up with a process that is more sustainable.
Thank you. And so people should go to acs.org, right? And look for
/green chemistry, yes.
/green chemistry. Great. You can find out a lot more. And we're about to wrap up in time, but someone here wanted to know, made the point that it's an education revolution that we need.
Yes, and we are working right now to develop modules, curriculum modules for general and organic chemistry, which try and merge ideas of fundamental chemistry that's normally taught with green sustainable chemistry and systems thinking, all in the context of this sustainable development goals. So it's a 3-year effort, and I couldn't agree more that we need an education revolution.
Great. We'll just have one more quick question for Dr. Rao and then over to Neelam. So on your example of PLA versus PS, here's a question. In a perfect, which you said is not a Dow example, it's an example out in the world. In a perfect world, we would want to balance the economical, ecological, sociological impact against the sustainable safety, efficacy, and functionality of the product. However, especially at the start, this could come at a high cost. So what do you think is the most important factor to limit first or to start out first for further innovation? And maybe David, you can weigh in on that too, but Dr. Rao, you want to tackle this?
Yes, I mean, I have to sort of share my personal journey on this.
Great.
Because that's kind of guide how I participate in research. So in the beginning, I strongly believe PLA, for just on the simple topic or specific topic, I think that's the solution. PLA should be used. But more I think about it is we really need to try to keep the carbon in the circle. So if you consider the sun is free, other than that, everything is what we have. So if no matter where you take your carbon, you have to make the best effort to put this carbon into the place that can be used. So from that point of view, I do believe circularity is the key. So a material that both can be infinitely recycled as well as biodegradable will be my choice of material. And I don't think either one of them are the solution.
Okay. Well, thank you, everyone. I believe we're going to have an on-screen poll. Thank you so much. Thanks to everyone who asked questions. Sorry if we didn't get to yours, but we will be planning to do some additional webinars, and we'd love you to vote right now. Let's see. If you're an attendee, please select what topic you're most interested in next for a specific sector for a webinar, because we're interested in all these areas, but we'd love to know your preference. And with that, I'm going to turn over to Neelam Vaidya, our CEO. Over to you, Neelam.
Thank you, everyone, for joining the webinar, and thank you, Yan Chao and David, for giving your wonderful insights to the group. Today, we heard that rather than disposal focus, you should think about circular economy, reusability. And Dr. Rao also mentioned that sustainability is the opportunity for green chemistry revolution. I love that. I would like to point out that we will be having, as I mentioned before, that future webinars where we will focus on specific sectors or industry and bring in the experts from those industries. And so stay tuned. We'll be having these webinars hopefully every 6 to 8 weeks. And thank you again for joining us.
I really enjoyed the conversation. Thank you.
Thank you.
Yes. Thank you.
Thanks, everyone. Bye now.